Okay, this video is about linearity, and in this video we will provide a definition of the two conditions that must be true for a system to be linear. Those two conditions are homogeneity and additivity. A system must be both homogeneous and additive in order for it to be linear. So we'll describe mathematically what those two things mean. We'll try to provide some intuition about what they mean, and then either in this video or the next we'll have some examples of trying to actually determine if a system meets those two conditions. So the first condition that we're interested in is homogeneity. Okay, and homogeneity can be described in this way. Suppose we have a system and the input to this system is x of t, and the output in response to x of t is y of t. Okay, so a homogeneous system or a system that is homogeneous has the following property. If instead of x of t going in, I put some constant a, it's a real number, times x of t going in, if I get out a times, a times y of t, then the system is homogeneous. So conceptually what this means is if I have a particular input, so we've got a particular input here, let's just assume for now it looks something like a sinusoid, and this input leads to a particular output, say something that looks like this. I don't know why, that's ugly. I don't know why it would look like that, but, well, in fact, well, yeah, okay. If I take my input now and scale it by a factor of a, in this case let's make a be about 2 so the input gets twice as big, then the thing that happens to the output is it's twice as big. Oh, that's awful. That art is terrible, and that's a really ugly, that's an awful looking output function. But anyway, the idea hopefully makes sense. So the idea is that a system is homogeneous if you scale the input, and that leads to scaling the output. Okay, so that's the first condition that has to be met in order for a system to be linear. The second condition that has to be met in order for a system to be linear is additivity. Additivity. Okay, and a system is additive if the following conditions hold. So again, we've got our system. It's got an input and an output, and if I put some signal, which I'm going to call x1 of t, into the system, I'm going to get a signal out which is y1 of t. And I don't really, in order for the definition, I don't really care what the relationship between x1 and y1 is. I just know that there is that relationship. If I put a different signal, x2 of t, into the system, then I get a different signal out, y2 of t. Okay, so this is just setting it up. Now additivity means that if I take x1 plus x2 and I put that into the system, then the output of the system, if it's additive, will be y1 plus y2. So in other words, if, again, y1 is the response to x1, y2 is the response to x2, if I take then x1 and x2, add them together, and run that through the system, I should get y1 plus y2. So graphically, well, let's see if we can put together something that isn't completely hard to follow. So if I have an input, suppose that this rectangular pulse is x1, and the response of my system to x1 is maybe something that goes like this and then goes back down. Okay, so this would be y1. And I have as x2 maybe another rectangular pulse, but this one goes negative. Okay, so this will be x2. And let's suppose that the response of the system to this x2 is something that looks like this. So this would be y2. Okay. Now, if the system is additive, then if I put in a signal that's x1 plus x2, so that signal would look something like this. Okay, so this is the sum of x1 plus x2. Then the output of the system, again, if it satisfies additivity, should be the sum of y1 plus y2, which will look something like this. Okay, so again, if the system is additive, then I should be able to determine what the output of the system in response to the sum of two things would be.